block, let's compute the x-coordinate of the left edge. Note that MATLAB and Octave begin indexing at 1. Use this to extract an image patch from the left strip. Now find its best matching x position in the right strip, and finally compute disparity as the difference between x positions in the left and right images. Okay, let's run this. 6 disparity values as expected, but they don't make much sense, do they? Let's try to plot them. Okay, so what does this 0 in the first block position mean? Well, it just says that the best match for the block in the left image was found at the same position in the right image. How about the peak at position 2? This says that the second block has apparently moved a lot. You can actually verify this visually. Look at this feature in the left strip and its position in the right strip. Different blocks have apparently moved by different amounts. Now, how do these disparity values relate to depth in the scene? Think of what are the drawbacks of a simple approach like this.
We've taken a look at correspondence done in a simple fashion. And in fact, that simple fashion is what you guys are going to do on your problem set. I want to take a look at a couple of slightly more sophisticated methods that are actually closer to the state of the art in stereo. There are a couple of ways we do that. There's a bunch of stereo pairs out there for which there is known ground truth of depth. So here's one from the University of Tsukuba. It's a well-known scene, and the image on the right is the actual depth. And these things can be generated a variety of ways. You use a laser scanner, some other method of being very precise in doing the matching. But the idea is, if you're developing a stereo algorithm or you're doing a paper or something, you have a scene for which you can say, I know what the actual value should be. So the types of methods I was showing you before, which are window-based matching. On the left here, we have sort of the best result of a window-based match, and on the right is the ground truth. And we're using a false color image here. It makes it a lot easier to see mistakes. If everything was just gray values and disparities, it's harder to see how things have changed. And you'll notice that it does an okay job. You know, the mannequin head is in front of other things, but it really does a pretty crummy job around the edges. This movie camera in the back, whoops, bad color. This camera in the back is sort of all eaten up here, never mind what's going on over here. So it has some general difficulties. And what we'd like to do is to see if we can get a lot closer to that ground truth solution. So better solutions do something more than just individual correspondence estimates. All right? Essentially, what they want to do is they want to optimize the set of disparity assignments in some sense jointly. Meaning that I don't just assign this pixel to somewhere and then this pixel independently. I want to think of all of the assignments together in some way and come up with an optimal solution. And this can be done at least two different ways. One is to do a scan line at a time. So we're still going to do a line at a time, but for all of the pixels in that line, we're going to think about how we want to do the assignment, and then we do that for each scan line. And then even more modern methods, and ones that get even more improvement, they actually do it on a full 2D grid. So we're not thinking just across the scan line, but vertically as well. So let's talk about the scanline methods. So here I have that Tsukuba University picture again, and we have two intensity profiles, the left and the right. All right? So just to be very precise about it, we have a 1D signal here and a 1D signal here, and we have to match every pixel here to some pixel somewhere over here. All right? But what we want to find is we want to find the best overall match. That is, the whole set of matches, we want the best set. So the way this is done is in what's called a dynamic programming formulation. And it's a little complicated, but bear with me. So what we have here is, I'm going to pretend that I've got the left scan line signal down here, and each of these is supposed to be the pixels, although I notice there are more dots than pixels, so assume that there's as many squares as there are dots in this grid, and same thing over here. And let's assume for a moment that we know that the leftmost pixel here corresponds to this one, and the rightmost pixel there corresponds to that one. All right? Well, then a solution to the mapping of the left to the right is just a path from that top left-hand corner to the right bottom right corner. So there's a particular path, okay? And the goal is to find the best possible path. and best possible path meaning the least cost. Now, when you're located somewhere in this grid, there's only 3 different ways that this path can go. The simplest way is when you go on the diagonal. Now, when you go on the diagonal, what it means is if this pixel was mapping to this one, then this one is mapping to the next one. That is, they're staying at the same disparity. So if I have to go +3 to match this pixel, then this one's also +3, and I just keep going along. But suppose I have some pixels that are visible in one image and not visible in the next. So here I have an area that I'm saying is left occlusion. What I mean by that is visible to the left eye and is not visible to the right eye. So what that means is that all of these pixels, this range here, are all being mapped to this one location. So you can think of it as that this pixel was mapped to this pixel, but all of these were not seen. So that's a left occlusion. Correspondingly, you can have right occlusions. All right? And the goal is to find the least cost through. Now, when you're going diagonally, your cost is just the match between 2 pixels. And that can be a match much like we did before. Did normalized correlation or sum of square differences, depending upon whether you're doing similarity or dissimilarity. But when you're not going the one-to-one, but you're actually doing the occlusion, what you need to do is pay a price for occlusion pixels. And a variety of methods have been designed that tell you, that say how to try to assign that cost. Some of them are Bayesian, some other ways. Now, for those of you that know about shortest path or Dijkstra algorithms or other forms of solving this, this can be formulated as a dynamic programming problem. And dynamic programming approaches are nice because they're computationally efficient. You don't actually compute all possible paths, and yet you can still compute the best possible path. And the only thing requires is that you basically have to be able to evaluate the costs of going horizontal, vertical, or diagonal. And here I've listed some references, including one by this Bobick, that showed about how to do that. We introduced this thing called ground control points, which was a cool way of not being very sensitive to the occlusion cost value that you use, which was part of the problem of earlier methods. But this is in the waybacks. Looking at that Tsukuba University thing again, here you can see that with the dynamic programming, we get a lot better solution than we had before. Things are doing better here and quite a bit better there. But one of the things you'll notice is that you get these streaks. And that makes sense because every scan line is done independently of the other scan line. So it doesn't know anything about the previous solution. So it makes sense that as you change scan lines, you might actually get a reasonable shift. And unfortunately, you can't use dynamic programming to find a spatially coherent set of disparities over a 2-dimensional grid. You have to do another approach. So in motivating that other approach, let's think about it this way. What defines a good set of correspondences? Well, first of all, going back to our earlier work, we want each pixel to find a good appearance match from left image to right or right to left. So we talk about match quality. But the other thing is, remember when we were first doing filtering for noise, we said one of the assumptions we make is that 2 pixels that are nearby have similar sort of real values. Well, when you talk about depth, you can also talk about how 2 pixels that are nearby have a tendency to have approximately the same depth. So that means that they probably should have about the same disparity. So if this pixel has to be shifted over 4, the one nearby shouldn't shift a whole lot. Okay? And I might want to penalize solutions that have lots of jumps. So the method that we're going to use now looks at both of those things. And it thinks of solving stereo as an energy minimization problem. The first term, the energy I should define that here we have I1 is the left image, I2 is the right image. We've got a window on the left. We're going to look at it across the right. But then all the way on the right is a disparity image. Okay, so that's the disparity that we compute. And our energy as minimization approach requires 2 energy terms. The first term is a data term. And the data term just says that summed over all the pixels, that the window subtracted from the window on the other image, so this window minus that one, squared, should be as low as possible. So we want, if we're going to do an energy minimization, our data term basically takes a look at the squared of the differences. That's similar to what we were doing before. So one way of thinking about it is when we were doing correspondence through dense search, we were only looking at the data term. The second term is called the smoothness term. And you'll notice that I don't have any window here, I don't have any window here. I'm only looking at the window over here. And in fact, in the smoothness term, you'll see that the image doesn't come in here at all, neither the left or the right. I'm only looking at the windows of the neighbors in the disparity image. This is the disparity image here. All right. Now this row function, this is a function that's essentially a robust norm. So what you want is, it's okay to make small amounts of change, and then it should get expensive to make large changes, but it shouldn't get even more expensive to make even bigger changes, because that's going to be sort of a jump at an occlusion. So that row function is meant just to be a robust, I mean, you can think of it as a square that maxes out. But that's our smoothness term. And for energy minimization, what we do is we have a total energy, which is a blend of the data term and the smoothness term weighted by these coefficients. And what you want to find, and this is the hard part, is you want to find an assignment of disparities that minimizes this energy function. So the bad news is that it's hard to do. The good news, no, that's not right. It's not hard to do. You're master students in computer science. Hopefully some of you have seen the graph cuts algorithm. I'm not sure. We may do that later in this class when we do an algorithm thing for segmentation. Graph cuts is a well-known computer science algorithm where you've got two groups of graph. You have a graph and you want to cut it in such a way that minimizes some value. The cool thing was that Bobick, Wechsler, and Ramanzavi applied graph cuts to some computer vision problems, and in particular, they applied it to this stereo disparity problem. And when you do that, you get a result that looks like this. And this is pretty good. So on the right here, we have the ground truth. All right, and on the left, you have a picture that looks pretty close to that ground truth. There's still a little bit of issues. I guess green's a bad choice here. Pick red. There's still some issues around here, and of course a little bit with where the occlusion happens. Because remember, we've got occluded pixels near the edges. But in general, compared to that correspondence solution that I was showing you before, it's a much better solution. I also point you to this Middlebury stereo website. There's a whole bunch of ground truth and sort of standards in stereo that's available there. I don't want to give you the impression that stereo is a totally solved problem. There are still some challenges. Textureless areas, it's very hard to know exactly where the match is, and clearly the surface has to have more influence. Occlusions are still a challenge. Violations of the brightness constancy, so things like specularities whose position on the surface move as I move, that violates our stereo. Really large baselines, so I've got a camera way over there and a camera way over there. Well, now I've foreshortened things, right? So here I see the front of the camera, and over here, probably I'm out of the field. Probably Meg can't, I'm totally gone. Well, but all I see over there is the side of the camera. So if I wanted to do stereo matching, that's a very hard thing to do. And then there's camera calibration errors, right? So remember the camera calibration defines for me the epipolar lines. What if they're wrong by a little? Well, then my epipolar lines are wrong by a little. So how do I deal with that? So these are challenges for ongoing stereo research. So that ends the lesson on stereo matching. In fact, that ends all of our lessons on stereo. You're going to implement the simple correspondence method. By the way, for a more advanced version of this class, we asked to do the energy minimization by either implementing or using a library for graph cuts. If you're so disposed, you might find that a really cool thing to do. When you go to implement this simple version, hopefully you're going to be impressed by two things. One is, it doesn't work nearly as well as I implied it would work, and I even didn't imply it would work well at all, so that's really going to be. However, your computer will be seeing in 3D. You're going to give it two pictures, we provide you the pictures, and your computer will recover the depth. You know, up until not that long ago, that was considered magic done by human beings' brains that was not understood. And now you can do it on your iPhone if you had two cameras. Anyway, I hope you'll find it cool that you can recover that depth. That ends for stereo. Talk to you soon. Welcome back to computer vision. I hope it's welcome back, because if you're jumping in now, you missed some really good jokes in some of the better lectures. This one's okay, actually. All right. Anyway, today we're going to talk about extrinsic camera calibration. We'll define what that means in a minute. We took a little hiatus to talk about stereo, so you guys could get working on your stereo. And stereo was our first look at multi-view geometry and multi-view cameras. And we talked about how, in order to do real depth reconstruction,